Hello everyone, my name is Luming and I'm a PhD student in Colorado School of Mines. I'm very sorry that I cannot physically show up on this conference. Please bear with me a little bit. Today, my talk is about a new local shape descriptor named Geodesic Spin Contour. This descriptor is designed for matching shapes with near isometric deformations, especially for partial data matching. This research is conducted by me and my advisor, Andre Shimchak, and also my dear colleague, Dr. Wei, in Chinese University of Hong Kong. In this talk, I will cover briefly what is the geodesic spin contour, how we compute it and use it, also how well it performs comparing to other methods. Okay, these all geodesic spin contours show on different locations of the human crane data. You can see that different places have different this kind of contours, which is good. Before I move to the detail of how I get them, let me show you why we designed this descriptor first. So this descriptor is designed for finding correspondences between two shapes. Generally speaking, many methods first use the local matching to select some initial set of correspondences, and then use this local match in the global match, which is consistently find the full correspondence. So in this talk, we will only focus on the local matching. And this kind of descriptors, for example, we have spin image and also heat kernel signature. And so from the name, you can see geodesic spin contour may have some relations between spin image, which is correct. We generate the spin image to isometric case so that we design which is called geodesic spin image. So our method is truly closely related to spin image. And for local descriptors, we should have several different requirements. First, it should be local support, which is only used a limited portion of the data around the specific points, and it should have good descriptiveness and invariant, which I have shown in my second page that you can see in the human crane data. Different places have different kind of these geodesic spin contour, and also, which is I have not show you, is that our descriptor is robust to contamination. Especially here, I will mention for some missing data and partial data, our descriptor performs pretty good. And here, I want to stress that find the correspondence, the key for doing that, no matter global matching or local matching, is to find invariants. And using that invariants, we can design different descriptors, we can design different kinds of global matching method. So I will stress that several times, that our descriptor is based on some ideas of finding the correspondence of the invariants, using the invariants, and also like find the relationship between different invariants on the different deformations. For example, let's revisit the spin image. Here is a fantastic model, and I pick a point here, and the spin image looks like that, which is projected of every vertex to a field, which here alpha and beta is defined as the projection of the Euclidean distance, because originally spin image defined in 1997 is by Johnson and Hubbard is to use the Euclidean distance to define a view as a descriptor, which is a 2D image, because in rigid registration, the shape is assumed to be rigid, and the distance, Euclidean distance, is the basic invariant here. So we can see in this figure that alpha and the beta are projections of the Euclidean distance. one to the tangent plane, another one to the normal direction, and it's suitable for rigid registration. However, not all these Euclidean distance can be used on another type, for example, isometric deformation. Here, this two human is only rigid rotated, so the invariant between the hand, finger, and the toe is the Euclidean distance. We can use a lot of Euclidean distance pairs between different parts of this human as the invariants to design descriptor, which is how spin image comes from. And here, how about the asymmetric transformation? Clearly, you can see the distance between the finger and the toe is changed, the Euclidean distance. What is unchanged? What saved us is that we still have the geodesic distance. You see here, the geodesic parts, the length of them, more or less the same. We can call it neo-asymmetric shape deformation. So that comes up idea that by replacing the Euclidean distance in spin image, which is used for rigid registration, can we design another descriptor still locally, but just replace the Euclidean distance as geodesic distance? And the answer is positive. So look at here. The spin image used the Euclidean distance. You can see q minus p, which is actually a vector pointing from vertex q to vertex p. And by replacing that as some intrinsic distance, for example, the geodesic distance, or we come up a new descriptor. Here I choose alpha as the average geodesic distance pointing out from Q, and beta is the geodesic distance from the particular point P to Q. So by doing that, we create the geodesic spin contour. So the idea can be shown in this graph. So you can see this is a Tosca Santua model, and we pick a point on the fingertip. We can draw a spin image. By replacing the alpha and beta to the average geodesic distance and geodesic distance from the particular points to every other point, we create a geodesic spin image. It's still an image, and we move one step forward to create a new descriptor. Here, we call geodesic spin contour. You can see that this is the outer contour of the geodesic spin image. And we will then show you that why we choose geodesic spin contour instead of geodesic spin image. So in this set of figure, I will show you why we use geodesic spin contour instead of geodesic spin image. So for example, these two shape are isometrically, neo-isometrically deformed. So, and you can see the spin image correlation is very poor when we compute the cross correlation between these two spin image. The correlation value is less than 10%. How about geodesic spin contour, which basically replace the alpha and beta, which is the normal and the tangent projection of the Euclidean distance, to average geodesic distance and the geodesic distance, which is unfortunately the correlation still less than 30%. Ideally, we hope the relation between these two images should be 100%, at least as high as the beta. But why we get this correlation less than 30%? It's because the cross-correlation value is dominated by the high value pixels. You can see I have two white arrows here. You can see that this high value portion is off by several pixels, which makes the correlation value between these two geodesic spin image is pretty low, even they look similar. So we choose to use contour. And clearly you can see we cannot use cross-correlation as the comparison again. So we may have some other method to compare these two contours. But right now you have a rough idea that why we use contour, because it's not so sensitive to the place where the high pixel value determined. So by looking at this geodesic spin contour, we may also introduce a fast implementation and a suitable matching method. And also I will show you the evaluation in the last step. So the idea is first compute the geodesic spin image and then get the geodesic spin contour. But you can see that this will be a very slow implementation because we need to first generate the spin image, geodesic spin image, and then we never use them. But because what we use is a geodesic spin contour. How about we generate the geodesic spin contour directly from the shape? And I can tell you this is possible. And from here, we will tell you a fast implementation. So to compute this geodesic spin contour at a particular point, like I show you on the board, like on the fingertip of the sand tool, first we need to determine the range of the beta, which is the geodesic distance to the particular point. And then we sample this to generate some geodesic isolines. Then we loop over triangles and compute intersections. So think about that. We have a particular beta, which is an isoline in the shape, and also in the image domain, it's a particular beta. We have a lot of alpha intervals. And after we compute the alpha intervals, we connect the discrete point to form the final contour. Here I will show you how we connect the intervals. First, we get these kind of intervals. The vertical axis is the beta, and the horizontal axis is alpha here. We will first loop over the beta from top to bottom and connect the top contour. And then we loop over the contours, the beta from bottom to top and connect them. So you can see here we form a closed contour. This is pretty useful and important. Without connecting them, we will get a very big arrows, even if these two contours is close enough. And still, remember that every local descriptor should have a local support. So we must make two local versions of our alpha and beta. First is alpha. We use the local average geodesic distance. By here you can see we set a radius r, and we only choose vertex that is inside this radius, and average them with the area weighted. The big A here of Q is the area. And we have a local support of the length L, which means we only use the points that has a geodesic length which is less than L to compute the local geodesic spin contour. And for similarity measure, we use the L1 distance. which is defined here. This distance looks like a warped version of the contour to another. It's not a Euclidean distance. So after I show you how we come up this contour, in this portion, I will show you how to evaluate it. First, I will show you the robustness of this contour, and then I will show you some comparisons to other state-of-the-art methods. By robustness, I mean how this descriptor perform on partial data or perform on some other data with various resolution. And comparisons, we will do qualitative and quantitative comparisons. First is the robustness. Here is a WRF from the Tosca data, and you can see this WRF have 8644 phases on that. And this is the associated geodesic spin contour at this point, which is indicated by the gray ball here. And if we clear some phases from the WRF, how about this new geodesic spin contour? You can see looks like that, which does not change too much. And how about if we force doubles the phases, and its geodesic spin contour still looks like very similar. And for other comparisons, we will compare to some other method like spin image, which is most closely to our method. I admit that this spin image is not so suitable for non-rigid registration, so we will use a local version. And other three, like HKS, WKS, and intrinsic shape context, is well known in isometric shape matching, and is designed in these recent years. So first, I will show you qualitative comparison. So look at here. First, I have two different horse models with isometric deformation. And for the source mesh, which is on the right, I cut the tail of this horse and pick a point on this mesh. And also pick, I know the ground truth on the target mesh. So the point indicated by the arrow is first picked out and compute the descriptor difference to every other point on the same mesh and also on every other point on the target mesh. So you can see I show here color mapped is the descriptor difference, which is for HKS, which is just signal difference. You can see that from the source mesh, the source point, what is the closest point on the target? It's not on the correct place. You see the blue regions move to the butt of this horse, which is incorrect. And the same thing happened in WKS. And it's even clear that WKS cannot match the source point to the right place. But geodesic spin contour can solve this problem and can tell you that the closest point for this source point is still on the ground truth point on the mesh, on the target mesh. And so qualitative comparison is totally not enough. From now, I will show you some quantitative evaluations. The first I will use is the hit rate. By hit rate, I mean I will sample one mesh and find the descriptor differences from the source mesh to the target mesh and pick several different points on the target, like different amount, to see how the hit rate changed, the hit times changed with the change of the amount of points I choose on the target mesh. And also I will show you the average geodesic errors between the source and the target matchings. So here I want to emphasize that not only the hit rate is important, but also the average geodesic errors show some meanings here. Because we don't, even if we got an error match, we don't hope that this wrong match is too far away. So for here, these are two human crane data. It's a MIT crane data, which is public available online. On the source mesh, which is still on the right part, I sampled 50 points, used farthest point sampling. And for the right data, the source data, I cut a hand and cut a feet, which is a partial matching here. So you can see that the hit rate, both the hit rate here, the geodesic contour, spin contour, GC here, has the highest hit rate. Spin image, local version, has a low one. And WKS performs a little bit better than hit kernel signature, but is still inferior to geodesic spin contour. And geodesic spin contour has the smallest average geodesic errors. And another test is on comparing the sparse and the dense Tosca-Wolf data. You can see one has merely 2 times larger number of vertices. And still, we compare to wave kernel signature and heat kernel signature. Geodesic spin contour is the best on both hit rate and errors. In addition, we compare the performance of geodesic spin contour to other methods on different WRF data with some part of carting. Note that this cart is not on the major part, which is spread all across this WRF model. So you can see we cut more and more. How it performs? Geodesic spin contour is still the best, which is the black lines on both hit rates and smallest geodesic errors, which means this descriptor is very stable on this kind of data contamination. So the last one, I will compare a method to some new method called intrinsic shape context, and on this Tosca Stantour model. First is on the full matching, the hit rate, and errors. And on this kind of cut, which is cut the whole part of this central mesh, and the hit rate, the errors. So in conclusion, that our contribution is on first replacing the Euclidean distance with geodesics. We create a new isometric invariant intrinsic shape descriptor. And we find that using contours instead of images, which bring a large amount of stableness to our method. And also, we provide a fast computation and a measuring method. And all methods still have some limitations, and we can work further on this direction. This contour-like method opens a door of designing new descriptors in this kind. How about we don't use the average geodesic distance and geodesic distance, but use some other distance that is still intrinsically invariant on some other kind of deformations, which is possible. And I think not non-rigid registration can be concluded in neo-isometric. So we need to work out some other invariants can be used in some other kind of non-rigid registration. And it is possible to extend our method to other form of data, for example, point cloud or image registration. So if you have some questions, you can prefer to ask Dr. Wei here or email me. And thank you very much for your attention.